So welcome back, and just a quick reminder from last time, we have the official UIO website where you can find the basic information about schedule, etc. So this is the last time I'm going to remind you of these practicalities. You can subscribe to these services on the schedule. Carl Frederick is going to be here for the exercise sessions, which we have in the morning. We had already a good group of people discussing exercises with him. And then I'm going to put in messages here. These are basically the same messages which you see on Canvas, which we use also for hand-in. And you can ask questions there, etc. If you want to establish a discussion forum, you can use Reddit or other ones, but that is something which I leave to you guys. And then the same messages which you see here are also sent as a regular email with an update and plans, etc., etc. And then the other piece of practicality is obviously the GitHub site where you find basically everything. And those textbooks which I mentioned to you, which you can download for free from a UIO username account, you will also find the same textbooks if you now go into this folder here on the GitHub address, and you will find additional textbooks. So these are basically all textbooks which you can get from the university library. And some of the other textbooks are textbooks which are out of print. So I just had a PDF and I put it there. And clearly then you have the pub folder is the one which contains the latest update of the weekly lecture material. So typically if you go to week 2 here, which is this week, then you will find the Jupyter notebook and also the PDF. I'm not using the HTML anymore much, but the Jupyter notebooks and the PDFs are the type of teaching material which I use pretty often. Now, I'm going to switch also between the whiteboard and the slides. So let's just get started and quickly take a look at what we are going to do today. And as I also mentioned, I put the weekly exercises for the next week at the end of the weekly slides here. And these are typically exercises which we will discuss next week. And also next week, we will have a programming exercise where we are looking at the bell states, which we will discuss today, and how we can make a measurement on just one of the states and what that means for us and how we are going to interpret that. So let's switch over to the slides immediately. Let me find them. So it should be that one. So what we are going to have then today, we are going to remind you also some of the things we discussed last week. And in the slides from last week, there's a lot of material which I didn't have the time to go through because some of it is just basic linear algebra, which I hope you can just review by yourself. Now, the things which we looked at were the definition of a state vector, the notation which we're using, inner products and how to do an orthonormal basis. We looked at outer products and also tensor products. These are quantities which we are going to use repeatedly, again and again and again. So getting familiar with them is something which is just essential if you want to do quantum computing. That's some of the basic linear algebra. Essentially, what we are doing is actually applied linear algebra. That's to a very, very large extent what this course actually boils down to. And if you want to be a little bit, how to say, arrogant when it comes to quantum mechanics, it's very much applied linear algebra. Then what we are going to do today is to repeat some of the things from last week with tensor products and the computational basis very quickly. And then we are going to look at the Bloch sphere, which many of you may have encountered already. It's a very nice way to represent the quantum mechanical superposition for one qubit. And then we have the spectral decomposition theorem. Does that ring a bell for you guys? That's a very important theorem. And I will just remind you of that because we are going to use that one when we define the density matrices. And modern quantum mechanics is very much defined in terms of density matrices and operations with those. And especially quantum computing, when we are performing measurements, the density matrix is actually going to be very, very important. We are going to look at measurements, and then we are going to finally, the lecture today, we are going to look at a state which is entangled, and we're going to discuss measures of entanglement and what we mean with a pure state and a mixed state. So these are definitions which are also important. And entanglement plays an important role when we are going to write quantum algorithms, because these are the properties of quantum mechanics which allow us to perform operations with quantum computers, which you cannot do with classical computers. So entanglement, superposition, interference play a very, very important role. And these are topics which we are gradually going to sneak in. And also when we are going to simulate a quantum mechanical system with a variation of quantum eigensolver, this is an algorithm where we are going to use entanglement explicitly. Okay, so that was a little bit about some of the things. And I have this textbook by Scherer, which you can access again, which is very nice if you just want to look at the mathematics. We have the other textbooks, which I mentioned last time, by Olivares, and there's a textbook by Hund. There's actually a whole plethora of textbooks. And these are typically the kind of reading recommendations I give week by week. And then the Zoom link. So I just wanted quickly now to switch over to the whiteboard and remind you of some small practicalities about the way we represent states and what we mean by a computational basis. So let's switch over to the whiteboard and take a look at some of the properties and things which we discussed last time before we move over to the Bloch sphere, measurements, density matrices, etc. So a very central topic which we need to deal with and which we always have is a so-called computational basis. And for one qubit, the typical computational basis, and we are going to stay with a one qubit basis for some time. This is now defined by two states. This is a binary system, and you could think of that as a vector 1, 0. And then you have the other vector 1, which is given by 0 and 1. And just as a quick reminder, if this is our Hilbert space, this is an orthogonal basis, and it's also a normalized basis. And we normally call that an ONB, orthogonal and normalized. We often just shorten it to orthonormal. Now, that's the computational basis. This is also a classical basis. There is no quantum mechanics here. It's when we start using the systems in terms of quantum mechanical states and manipulate them that we actually start talking about a basis which you can perceive as something different from a classical basis. So when I call this a computational basis for one qubit, we will also refer to that as a classical basis. In principle, there's no quantum mechanics here, right? And then we know that we can make states which are a linear combination of that. And I'm going to stick to the Dirac bracket notation. And when we have an orthogonal basis, we can always expand a state in that basis. Now, there are three important matrices which we are going to use again and again. We can also, with this basis, we can make tensor products of additional states. So we can actually have a 2-qubit basis. Let me quickly remind you of that from last time. And we could now couple a qubit in a system A with a qubit in a system B. So we could think of 2 qubits being in the state 0, 0. This is something which we will write in a more compact way as 0, 0. And this is given by the tensor product of 1, 0, of 1, 0. So we are starting with a binary system, but then we end up a system with 4 states, which are also orthogonal. That's also a classical computational basis for 2-qubit system. So in this case, this vector here becomes equal to 1, 0, 0, 0. We can set up a new state, which would be this one with 1 in system B. And that's essentially us taking 1, 0 and tensor product with 0, 1. And we know that when we do the tensor product, this becomes 0, 0, 1, 0. No, sorry. Not there, that one. And we will typically write this one as 0, 1 in a more compact way. So often when you look into textbooks, we tend to suppress the tensor product notation, and we simply write things in a very compact way. Later, when we are going to look at the algorithm for quantum Fourier transforms, we will relabel the state 0, 0, which we have here, with just 0. And then we can use bit operations to find out which is the state 0, which is the state, this will be state 1, etc., etc. But this is something which we are coming back to. And then we have two more states, and one is this 1, 0, which is simply system A. So sometimes we put labels and sometimes we don't do, just for simply for not having too much notational clutter. And this would be a state which is 0, 0, 1, 0. And we would typically label this one, as you saw here, 1, 0. But this is essentially the tensor product of the 1 of system A and tensor product with 0 of system B. And finally, the last state, which is 1, 1, which I'm just going to write out like this. This is a tensor product. And this is actually 1 tensor product with a 1 in system B. So in many of the quantum mechanical algorithms, which we are going to encounter when we often do these operations, we are often thinking of A and B as different systems. However, nature often doesn't allow us to do that. So that's something which confuses people, because often we will deal with electrons, which could then be trapped in different potential wells. And you would think of each such potential well as system A, another system B, etc. But since these are fermions, in principle, they are identical and indistinguishable particles. So this kind of notation here is something which we often tend to skip with A and B, especially when we are dealing with identical and indistinguishable particles. But this is something which should come out from the context, what we mean by this specific state, okay? So now I'm just going to introducing the notation here, because this specific notation allows us to write out the states in a more compact way. Now, then we also have important matrices, and we have these Pauli matrices. So let me quickly remind you of that. So the Pauli matrices, we have the Pauli Z matrix. So let me just introduce the notation immediately. And we're often going to write it like Z. This is pretty common in the literature. And this is a 2 by 2 matrix, which is simply -1 and -1. And then we know that if we take the 1 qubit operations with these Pauli matrices, we know that if we act on the state 1, 0, this is simply us doing 1, 0, -1. And if you then do the plane linear algebra operations, you will see that this is +1 multiplied with 1, 0. So what we are seeing now is that this Pauli Z matrix is actually a matrix which has as an eigenbasis the computational basis we have chosen. So if we act on this with 0, 1, you will see that the only thing is that we have an eigenvalue, which is -1, but then we have 0, 1. So the Pauli Z matrix is very interesting, because you will see that when we are going to write out the Hamiltonian, which previously can be written in either first quantization or second quantization with creation and annihilation operators. We are going to rewrite the Hamiltonian through a transformation, which is the most standard one, is a Jordan-Wigner transformation, where we transform creation and annihilation operators into Pauli matrices. And then when we are going to make a measurement, so keep that in mind, because this comes a little bit later, when we make a measurement, we would like to make a measurement in the computational basis. So that means that some of these matrices here can actually be transformed. So if we take a Pauli X and a Pauli Y matrix, they can actually be transformed by specific operations. We are coming back to that in terms of a Pauli Z matrix. So keep in mind, this is a very important aspect because we have chosen a computational basis. So if it's a 1 qubit basis, then this is a natural computational basis. But there is nothing which hinders you of having this one as a computational basis. And then you will see that this basis here, depending on the variables alpha and beta, can actually be an eigenbasis of the Pauli X plus the Pauli Y matrices. So this is a small exercise I'm going to give you. So but let's continue a little bit with the computational basis and these matrices. So we have another famous matrix, which is the Pauli X matrix, which is simply 0, 1, 1, 0. And then we see that if we act with that one on a given state, like the 1, 0 qubit state, we see that this one is actually something which changes our state to a 0, 1 state. So this gives us actually just the qubit 1 state. So you see now that this is definitely, because what we started with is a 0 state, and that gives us simply +1 and the qubit 1 state. So you see now that the Pauli X is not a matrix which has the computational basis as an eigenbasis. So this is the same thing you will also see if you now take the Pauli Y matrix. So the Pauli Y matrix, sigma Y here, or Y, is equal to, and then this is a complex quantity, so we have 1, and this is minus I and 0. And then I leave it to you as an exercise to act with this one on the computational basis. So these are very important matrices. They have also commutation relations, which you also played around with in the exercises here. So let me just look up my notes a little bit and see if there's something I've forgotten. Yeah, so one of the exercises which you can do then is to find the right linear combination of these operators. So now the states here, so you can actually make a state which is a linear combination of 0 and 1. And then you can find that these are actually eigenstates of a combination of the Pauli X and the Pauli Y matrix. So this is probably something which you have seen in exercises in quantum mechanics. So it's a useful exercise to actually sit down and run through these things. But just the basic message here is that we are defining a computational basis. Typically for 1 qubit, it would be this one. If we have a 2 qubit basis, this would be our computational basis of these 4 states. And you can easily convince yourself that this is a basis which is orthogonal, and it represents the 4 possible ways. You can obviously make linear combinations. And we are going to do that at the end of the lecture today when we introduce the so-called Bell states. Okay? So there's another quantity which is very nice to introduce, and that is the so-called Bloch sphere. So is everybody familiar with that? Have you heard of that? So let me introduce the Bloch sphere, because you can make this state which we have here, this first state, which is a linear combination. We can write this in a more general way. And this is very nice if you want to represent the kind of superposition you can produce when you are doing quantum mechanics. So keep in mind now that the states which you have here, they are states which you can think of as classical states. But quantum mechanically, we can make a superposition here. And there's a nice way of representing this superposition in terms of spherical coordinates. So let's quickly introduce that as a technicality, which is also interesting for later when we are going to look at the variational quantum eigensolver. So this is the Bloch sphere. So what we can do now without any loss of generality, when we look at this specific state psi here, which is a linear combination of the computational basis state 0 and the computational basis state 1, this is something which we, without any loss of kind of generality, we can actually rewrite that one, this constant alpha, in terms of some number R0. So keep in mind now that basically everything which we deal with are complex numbers. So and beta could be written out as an R1 times E of I of phi 1. And that means that if we now want to factor out this angle phi 0, we could actually rewrite this state psi in terms of R0 times 0. So I'm just factoring it out. So and then we have an R1 of E of I of phi 1 minus phi 0 multiplied with 1. And then we can rewrite that one in terms of an angle phi, which we simply define as phi 1 minus phi 0. And where we would then have the constraints that this goes from 0 to 2 pi. And also that R0 plus R1 squared is equal to 1. Then you can actually rewrite this one in terms of the angles. So we have a psi 0, and this is given by cosine. And then we have theta half, where I'm just going to explain what the angles are, times 0. So this is another way of rewriting it, times sine of theta half of E of I of phi times 1. So this is a general representation of that state. And we know that the angle theta, which is the so-called azimuthal angle, is equal from 0 to pi. So this is a pretty general way of representing that specific state. And you see that when you want to calculate the norm of that one, that obviously due to the cosine squared and the sine squared gives you 1. So I'm just stating these things. And then I wanted to show you quickly how you can visualize this one, because now you're just using the quantum mechanical principle of superposition. And in the lecture notes for this week, you will find a Jupyter or Python code here, which we can actually use to set up the Bloch sphere. So let's just go back to the, so I should have it here. So this is essentially the stuff which we have been discussing till now. And if we look at, so let's just scroll down a little bit and look at the Bloch sphere here. So what I'm using is a software which we will also use, which is called Qiskit. So which is the software developed by IBM, which interfaces your Python codes with IBM's quantum computers. But you can run this without logging into a quantum computer. So next week, one of the computational exercises where we're going to deal with the Bell states, which is a 2-qubit system, we are going to see how we can actually use both Qiskit and write it ourselves. Now, in this case here, this is just a way to visualize this Bloch sphere. And then what you will see then, like in this particular case here, where I'm setting up a Bloch vector, which is 0, 1, 0. So you would see then that this points along this axis. Now, the state, which we call 0, the one computational basis state, you can think of that as the north pole of this Bloch sphere. So the values on this sphere are equal to 1. And what we are going to do, especially when we introduce this variational quantum eigensolver, or what we are later going to call parameterized quantum circuits, is actually to perform rotations of each qubit on this Bloch sphere. and then treat these angles as variational parameters. So we're going to vary a final expression in terms of all the parameters which reflect the rotation of one qubit on this Bloch sphere. Because we don't know exactly what the representation for each qubit is, but then we are going to have a set of parameters, which are the angles, which then will give us simply the different orientations. Now, one here, which is the, so you see now that if you think of U acting on this state with the Pauli Z matrix, you have +1 here, and you have -1 down here. So 1 here represents the South Pole, and that's the other computational state, the classical computational state. Everything else you have on the sphere here is a quantum mechanical superposition. So this is just one way to generalize these parameters alpha and beta, which we have. And finally, here you can actually use, you can plot the Bloch vector, and then you can specify the different angles and where you want it to point to. And then you can see now that this is a vector which points in this direction. Okay? And you're using spherical coordinates. So this is just one way to illustrate the quantum mechanical principle of superposition given a computational basis. Okay? Any questions to this? So there's another quantity which I now want to introduce when we go back to the whiteboard, which is also very important for us. And that is the concept of projection operators. So if you now look at the definition of the, we discussed these projection operators last week as well. If we now look at this one qubit system, which we have, so we have a state which we see as a linear combination of these two computational basis states. We can then define the identity here for this specific case. This is now given by the outer product of 0 and 1. And then we can define a projection operator which now projects out the state 0, which we also defined last week. This is just 0, 0. And I'm just going to write this for now as an operator P. Now, one thing you see here is that P squared is equal to P. So we normally call these for idempotent operators. And we can define a new operator, which we call for Q, where also Q squared is equal to Q. It's actually easy to see that. And this is given by the outer product of these guys. And you can quickly see that this is 0, 0, 1. And this is also an idempotent operator. The identity then is just equal to P plus Q. I'm trying to keep these hats on it because later I will use P for probability. So P with a hat on is an operator here. And you'll see, as we also did last time, if I act with P on this state psi here, that simply projects out the state 0. So that gives us alpha times 0. And then I can have Q acting on psi, and that gives me beta times 1. So what I'm doing then is to project out a specific state. This becomes very important when we now are going to look at the definitions of measurements. There is another quantity which we are also going to need, and this is the spectral decomposition of an operator. So this is a technicality, and some of you may have seen it, some of you may not have seen it, some of you may have seen it, and you may have forgotten it. So let me quickly remind you about the spectral decomposition of an operator. And this is something which, because we are going to, when we introduce a density matrix, we are going to use the spectral decomposition theorem. So let me quickly remind you of that, but I'm going to first go back to the slides because you will find this information in the slides, in the weekly slides. And this is the quantity which I just quickly wanted to remind you of. So this is the so-called spectral decomposition of an operator. So what we are, so this is an important technicality, and it's a technicality which we will use again and again. So we know that we are dealing with unitary operations. We are going to mainly look at these systems as isolated systems, or if we have the environment, we were going to couple the environment with the system and look at that as a unique system. So that means that no particles are going to escape, unitarity is going to be preserved. So we will essentially in this course deal with unitary operations. Now, we know that we have an operator which could have a state psi as an eigenstate. We can typically rewrite it like that. And this is the kind of solution which we have seen many, many times. So by finding the characteristic polynomial, by setting the determinant equal to 0, we can then find the eigenstates of the system. Now, if you now define an orthogonal basis, so our computational basis, and this basis could now consist of more than one qubit. So this state 0, which you see, could be a 2-qubit state. Then we would have 4 basis states. If we have a 3-qubit system, we would have 8 basis states, and so on. So now we are looking at the binary possibility, so that means that the possible number of states is 2 to the power of n, where n is the number of qubits. So that's the total set of configurations which you can make. And in this specific case, we have an orthogonal basis, which you could think is an eigenbasis of an operator A. And then it has also corresponding eigenvalues lambda y. You can then expand this a new eigenvector in that eigenbasis. So this is pretty standard, right? So nothing new here. So when we do that, you have also a normalization condition. When you act with A on this state, this is what you get. So there's nothing, hopefully there's nothing controversial and new here. This is something you have seen before. And this kind of operations are the kind of operations which we do again and again and again. With that, we can now, with the projection operators, we can obviously now look at an operator which projects out specific components. So it could either be one which looks at the wave function itself, or you could just look at a specific component. So this is again back to this wave operator where you saw the example, the projection operator, where you saw the example with the 1-qubit case we had on the whiteboard. Okay? So when you do that, you know that when you act on this one, you're projecting out one of these guys here. So this is essentially what you get. That sounds okay? Then this simply results in when you act with this specific projection operator, then you project out a specific component with this quantity here, which is just a probability. If you square it, this is a probability of finding that specific component. Then when you act with A on this one, you can actually rewrite it as your eigenvalue. So if you go back here, if you take this one, so this is just the projection operator. This is your eigenvalue, which you're plugging in here. So you have the eigenvalue, and then you have the projection operator. That means that you can identify these two terms here as the eigenvalues of that specific state multiplied with the projection operator. What you have here is the spectral decomposition of an operator. Okay? So later, when we are going to look at the density matrix, which is a very important quantity, when we are going to look at the operations of quantum mechanical states, then the density matrix is going to be given by the probability of being in a state times a given projection operator. And that gives us a very compact way of estimating expectation values of quantum mechanical quantities. So how many of you had seen the spectral decomposition in different courses? So this is okay. Excellent. So I hope you can forgive me if I repeat things which you've seen, but sometimes it's good actually to see it again. It's easy to forget these quantities. So this is a spectral decomposition. It is true for any state, and it is independent of the basis. And the spectral decomposition can in turn be used to specify a measurement, as we will see pretty soon. if you consider two states, respectively, in the diagonalization process, you have obtained the coefficients alpha 0 and alpha 1, and beta 0 and beta 1. And then you can use an expansion in terms of the orthogonal basis 0, 1, and 1. And you can quickly see that. So I'm just showing you an example here. So suppose now you have this as a state, and this is another state, which are now linear combinations of your computational basis. Then you can construct the projection operator for the component A and for the state A and the state B. And when you perform the outer product, this is what you get. And similarly, you have the same for B here. So this is just still at the level of a 1-qubit representation. And then you see now that the density, the spectral decomposition allows you now to rewrite this operator A in terms of the eigenvalues, the outer product here, the eigenvalues lambda B, and the outer product of these states here. And this is what it looks like in all detail. So that's the spectral decomposition of this specific operator, which has this set of eigenstates and eigenvalues. Okay, just as an example. Now, what I want to do now is to move over to measurements, because this is what we actually are going to do. So when you run a calculation on a quantum computer, you're going to perform measurements on the system. And we are going to perform these measurements again and again and again. And this is actually the way you run a real implementation on an actual quantum computer. So you're going to have a state which is in a superposition, and that's the quantum mechanical aspect we are going to utilize. And then when we perform a measurement, the system collapses to a given state. And then we are going to measure again and again. And finally, we take the statistical average. So you can think of every measurement as a statistical observation, a sample, and then you calculate the mean value of all the samples. So that's the statistical analysis which we end up doing. So this is quantum computing in a nutshell. When you run things on a quantum computer, you're actually going to perform the operations of measurements again and again on the system. And then you simply collect the number of values you have and take the mean value of that. That's a statistical aspect of it. So we are going to look at, so the Bloch sphere, we already discussed that one, but we are going to look at measurements now. So let me switch over to the whiteboard. So the measurement part is something which we are going to see again and again. So suppose now that we have an operator A, and this acts on a state psi of A, and this gives us some lambda of A of psi of A. So this is just a basic statement which you have seen many, many times. So we have an eigenstates, eigenbasis of that one. Then we are going to define, again, these projection operators. So suppose now that we have a set of projection operators. And in this case here, we could now have a set of projection operators, which are called P0, P1, etc., up to a final one, P of n minus 1. And we know that the sum of these different projection operators give us the final completeness relation. So this is P of I. And the example which we have seen is the one with a qubit, 1 qubit, which is pretty easy to set up. So we had a 0 and 1 as a computational basis. And then we know that the 0, 0 is the one which we will define and have defined as P0. And that is simply given by 1, 0, 0, 0. This is just one example. And then I'm not going to repeat what we did before, but this is just an example. If we have 2 qubits, And if you have 1 qubit, if we have 2 qubits, then we would get 4 states, and then we can have 4 projection operators, etc., etc. Okay? So these are just definitions. Then we know that the probability of a specific state. So suppose now that we want to calculate the probability, and then I'm going to label that state as a state with an eigenstate lambda of I. This is something which we are going to define as the projection operator P of I acting on a state psi of A. So this could be any state. So psi of A is a state which I've chosen. And now I want to find out what is the probability of projecting out one of the components I. So this is actually, when we look at it, this is nothing but, if we use the standard bracket expressions for the expectation values, this is nothing but a P of I. So we are projecting out a specific component. And this psi of A could now be a linear combination of all these coefficients. So we could have a set of coefficients A of I, and then we have the computational basis I, and this goes from I equals 0 up to n minus 1 here, okay? So this is just a linear combination we are making. And now we want to find the probability of one of these components, okay? Now that these operators here, these quantities, they are idempotent, they are also Hermitian. So that means that if I take this one, I can actually write this as a P of I squared. And this is the same as a P of I, as we have seen before. So that means that if we just take this as an intermezzo here, it means that this result here is nothing but psi of A multiplied with this pi of A and psi of A. And the kind of notation which you see now, if you look at this notation here, this is essentially what we're doing. So this is just another way of writing that one. And then we know that the total probability is simply the sum of all the probabilities. So the total probability is now just the sum from I equals 0 to n minus 1. And then we have the probabilities of these lambda i's. And this sums up to 1, because we're assuming that the basis has been orthogonalized. Okay? Does that sound okay? Nothing? I hope you don't find this too boring, but I just wanted to bring in some of the definitions. So after the measurement, then we have a new normalized state. So after measurement, the system has then collapsed to a given state. And then we would have a new state. So after measurement, this is the post-measurement state. Then the normalized state, because we have to normalize it, the normalized state after the outcome of the measurement, this will be given by this P of I, which is acting on the state psi, and then we have to normalize it. And that means that we have a normalization constant, which is simply given by P of I of psi of I. Okay. So when we have performed the measurement, we are actually going to go from a superposition of many states, and we are going to project out one specific state. And this is the one we are going to target in a measurement in any quantum mechanical algorithm. So let's look at an example with the 1 qubit base. So I'm simply using the 1 qubit base, the 1 qubit base, simply because it's easy to do in the lectures. I can do 2 qubits, but then there are more matrices to deal with. So the basic principles, I mean, if you have it understood this one, then you know exactly what's going to happen if you have 2 qubits and 3 qubits, etc., etc. Then we have these operators, P1 and P0, 1, 1. And now we perform a measurement on a specific state. So let's do that. You will also see that if I sum up the P of i's, or P of I, you see that this sums to 1. It shouldn't be that difficult to show that. And now we are picking a state, which I'm going to call for psi, which is a linear combination of 0 and 1. So again, you could think of this as a state represented on the Bloch sphere. So we have the superposition of the two computational basis states. And then we're asking ourselves, what is the probability of finding psi in the state 0? So when I put a subscript 0, this is actually finding it in the state 0. And that should actually just be of psi, and then I should have P0 of P0. And this is again multiplied with psi, which is the same as alpha complex conjugate transpose plus complex conjugate, and then the state 1 multiplied with 0, 0. And this is again multiplied with alpha 0 plus beta of 1, like that. And if I do the math here, you will see that this shouldn't come as a big surprise. This is actually alpha squared. And then you can do the same with the probability for psi 1. So we are projecting out that specific component, and that is simply going to be beta squared. It's actually pretty easy to see that. So let me just add one more thing before we take a break. So if you then want to look at the state, the post-measurement state, so we would simply then have the following states. So psi 0, so this is the component 0, and I put a prime here because this has now been the result of a measurement. It's a result of a measurement, and this is simply given by P0 multiplied with the original psi, and then divided by the normalization constant, which is simply psi of P0 of psi. And this is actually equal to alpha times 0. So we're projecting it out. So this is the new state after the measurement. And then similarly, we would have a psi 1 prime, which is, and this shouldn't come as a surprise, is given by beta divided by the absolute value of beta multiplied with 1. So these are the basic expressions which we are going to deal with. And after the break, we are going to rewrite these expressions in terms of the density matrix, which will give us a very compact way of dealing with these quantities. I guess you've seen these things in one way or the other one, right? So the first lectures in this course actually meant to bring up some of the basic things you may have seen. And we are going to put it into the context of doing quantum computations and link that with specific quantum algorithms. But these basic quantities are things which we're going to use again and again. So you can think of this as the basic tools for many of the operations which we will implement. So I went a little bit over time, but we should take a 15 minutes break. If you want to grab coffee, tea, you can go to the CCSE and refresh yourself, stretch legs, whatever. And feel free to ask questions during the break here. Right? So to summarize some of the things which we did before the break. So this is roughly where we ended before the break. So we are performing a measurement, and we have defined these operators, P0 and P1, which then for the 1 qubit case, project out either component 0 and component 1. So after the measurement, we are then in a new state. And then if we normalize it, this is what the expression is going to look like. And that's what we did on the whiteboard. And you could also, if you want to make it more complicated, you could have a 2 qubit system with 4 states, or you could have a 3 qubit, etc., etc. Then you would simply have to define the corresponding projection operators, which are then just the outer product of the different computational basis states. So in our case, the computational basis is 0 and 1. So this P0 is the outer product of 0. P1 is the outer product of 1. Now, if you want to formalize this a little bit, and this is what we're going to do now, because we are going to try to catch two birds with a stone. So we are going to use this expression for the measurement, and then we are going to introduce a density matrix. Now, what we did here, if you now think of the probability of a specific component X. So this is general. Previously, we had 0 and 1, but now you could think of X representing any of the specific components in the superposition of computational basis states. So that means that we are picking out one of these components. It could be 0, 1 for a 1 qubit case. It could be 0, 0 or 1, 1 for a 2 qubit case, etc. And this is what we have been calculating. But you see now that you can actually rewrite this in terms of this expression. And we are going to look at that on the whiteboard just to try to show you why this expression here is equivalent with that expression. Okay? And this is the one which is going to allow us to introduce the density matrix. Because this quantity which you see here is a density matrix for that specific state psi. That's the definition of it. But let me see if I can convince you that this transition from here to here is actually something which makes sense. And so let's try to do that, right? And go back to the whiteboard. So the quantity which we want to introduce now is the density matrix, because that allows us to write things in a very compact way. So let's define the density matrix. And then you will see that these operations which I showed you on the slides, this is something which we can rewrite as a trace of those operators, the projection operators and the density matrix. So if I now use the letter rho, and then I put a psi here to indicate that this is a density matrix for that specific state psi. And since we are staying with this 1 qubit system, so let me quickly remind you of that. This is equal to 0, now alpha times 0 plus beta times 1. And that means that if I take the outer product of psi, this is going to be given by a matrix where we have alpha squared, and then we have alpha times beta complex conjugate, and then we have alpha, same here, beta, and then we have beta squared, like that. That's the outer product. And let's just look at one of these operators. So what we have is P times P0, which is nothing but P0, and this is 1, 0, 0, 0. Let me just write this in a better way. And that projects out that specific state. Now, if I act with P0, so this is P0, on this row of psi, and put hat on it to indicate that these are operators or matrices. This is the same as taking 1, 0, 0, 0, and multiplied with the matrix which we have here. So alpha squared, alpha beta, beta, and then we have alpha, beta, and beta squared. So if I do that, what I'm going to get is then simply a matrix where the elements in the lower row are equal to 0. So this gives us, when we have performed the operation, that gives us simply alpha squared, and then alpha times beta 0, 0, 0. So what I see now is that if I now take the trace of this quantity, that is alpha squared. And we knew from before the break that this probability of psi component 0 was just alpha squared, right? We calculated that before the break, so let me just bring it up again. And this is what we did. We just used the quantum mechanical definition for a measurement, which was given by this quantity, and that gave us either alpha 0 or alpha squared and beta squared, if we were looking at the probability of the second component. Then you see now that if I take the trace of that quantity, we can actually rewrite this as the trace of P0 of P0 multiplied with the density matrix for this specific state which we have picked, the state psi here. And that is again equal, as you quickly can see now, to alpha squared. So in general, what we are going to have then is the following. The probability of a specific component X. So now I'm just writing this in a generic way. So this component X would be one of the components of this state psi in its superposition of all possible states in the computational basis. So now we're just picking one of the computational basis states. And we can write this out as the trace of this operator P of X, the one which projects out that specific operator, of P of X multiplied with the density matrix for that specific state, which we are looking at. Now, this is often written as, and you will see that in the literature quite often here. So let's just do that one. This is written out as an M of X, M for the measurement. So sometimes if you go into textbook, you will see that these projection operators are rewritten in terms of another operator. Any questions so far? Okay, so let's now look at the density matrix, because that's a very important quantity for what is coming now. So let's just bring back here. So this allows us to introduce a density matrix. And this is a quantity which also has many important properties. So we have a state psi, which we simply define as a linear combination. We have a basis, a computational basis, and then the CIs here are the complex numbers, which are the overlaps between the state psi and your computational basis I. So just as a quick reminder, C of I is simply psi overlap with I. Then what we are going to define then is the density matrix. So the density matrix for this specific state psi is obviously given by the outer product of these two states. And this is the same when you set up the calculations here in terms of a C of I squared multiplied with I times I. And keep in mind now that you have a computational basis. Now, this is nothing but the quantity which we called as a projection operator for that specific state. This quantity here is the probability of being in that specific state. So we can replace that one. And now this is where I have to be careful, because I'm going to have this P, which you see here, is supposed to be an upper key letter. And then I'm sneaking in the probability, which is a P of I here. And it doesn't have a hat. So C of I squared is actually given by the probability of being in that specific state. And now what you see now, if I take this and use the spectral decomposition theorem, or just the spectral decomposition of the density matrix, then you see that this density matrix can then be written out in terms of the probabilities. So this should be a lowercase p, no hat on it, multiplied with the projection operator. And this is the same as I, or P of I, and then P of I with a hat on. And that is the spectral decomposition of the density matrix. So this is also a quantity which is going to make it, which is going to be useful when we are going to calculate the expectation values. So this quantity here, we're going to frame it in because we're going to use it again and again. Okay. This also has important consequences about the properties of the density matrix. And I'm going to bring up some of them via the slides here. So let's just do that, because then I can spend some more time on going back to the specific Bell states. So I'm going to look at the whiteboard again. What did I do now? I stop sharing screens, and I have my PDF here. Okay. So we saw now that we could rewrite this probability of being in a state psi of x in terms of the density matrix. And if we then just bring it back here, this is just the same calculations which we discussed. So we can write everything in terms of the projection operator and then the probability. And the density matrix is one of the quantities which is widely used in many of the more compact and modern quantum mechanical representations. And it uniquely describes the state of a given quantum system, both in an open system as well as in a closed system. An open system is a system where eventually your particles could leave. Suppose you have trapped electrons in a harmonic-like oscillator well, but this well is finite, and then the electrons could escape. So we would typically call this for an open quantum mechanical system, compared with what we would call a closed system. So we are going to introduce quantities which we will call for pure states and mixed states. And this has consequences for the way we measure the degree of entanglement in a specific system. And how we're actually going to run specific calculations, actually, and why entanglement is going to be such an important property. So what we have is this, which we also did on the whiteboard. So this is a density matrix in its spectral decomposition. This is basically what we did. So this quantity which you see here is also something which we can rewrite in terms of this trace. So the probability then, which we have here, is something which we now can rewrite in terms of the projection operators multiplied with the density matrix. And the probability of a specific outcome is something which we then would simply write in this more compact way for that given state, for that given density matrix. So I'm giving you some statements without a proof. If you go into the textbook by Scherer, the one of the mathematical properties of quantum computing, you will actually see the proofs for these statements. So I'm just, many of the proofs are not that difficult actually. So you can, the density matrix, we obviously assume that there is a probability which is larger than 0. So this sum of probabilities sum to 1, as usual. And then if you have an orthonormal basis, you can then define the density matrix in terms of this orthonormal basis, multiply with the probability of being in that state. Now from that, you can actually show that this density matrix squared is less than equal than 0, or larger than equal than 0, or less than equal than 1. And the norm 2 is always less than equal than 1. You can also define the state of the system collapses to after measurement. Namely, you can actually define this quantity here. So that would be the density matrix after a measurement. The density matrix of what we will later say is a pure state. So a pure state is a state which is uniquely defined. The state can be entangled or it cannot be entangled. But the thing is, with a pure state, we mean a state where we know exactly what it looks like. Okay? And the quantity, the density matrix is emission, positive semi-definite. All eigenvalues are non-negative. It's actually not so difficult to show that. It's an emission quantity. The eigenvalues are largely equal than 0. The trace is equal to 1. And you saw that from some of the examples we did with the 1-qubit case, that the trace of the density matrix is equal to 1. And given a probabilistic mixture of states, then you can rewrite it like this. This is basically the spectral decomposition, which we have discussed earlier. And then we can set up an expectation value of an observable X. And this is probably something you have seen in courses in modern quantum mechanics. Have you seen the derivation of these quantities before? So you would use a density matrix to set up the expectation for the expectation value for a given observable X. So that's a very compact way of expressing. If you have the state psi, then you can calculate this expectation value and the density matrix. So what we are going to do now is actually to look at an entanglement case and go through these Bell states, which we're also going to write a program for next week. And the program we are going to do is to write it ourselves with only basic Python libraries like NumPy, etc. And then we're going to perform the measurements and do operations on these specific states. And then we are going to, if we get time, this is something which can move into the week thereafter as well, is to also implement this on one of IBM's quantum computers, which we have access to. And in that case, we would have to translate everything using IBM's interface, which is called Qiskit. So we will, in the exercises next week and the week thereafter, we will play around with operations on a 2-qubit system. And everything we do here is relevant for the first project. So all the machinery you develop for the 1-qubit case and the 2-qubit case are items which we will reuse in the project. So when we have gone through these things here, the first 3 to 4 weeks, then we are ready to start looking at the variational quantum eigensolver and the elements which we need in the first project. Okay, so we need some, some baby steps here, which before we can move into the implementations of a specific quantum algorithm. So what I want to do now is simply to switch back to the whiteboard and slow down the pace a little bit. And we are going to look at the example of these type of theoretical items like the density matrix, the trace, etc. And we are going to look at that on a 2-qubit state. The reason why we do the 2-qubit state instead of the 1-qubit state is that the 1-qubit state is pretty trivial. And you've already seen many examples. So let's now move into 2-qubit states, and we are going to use this also to catch many birds with one stone. So we are going to look at what it means to be entangled, what a pure state means, what a mixed state means, etc. Okay? So let's stop this one and go back to the whiteboard. So I'm jumping a little bit back and forth. So the example system which we are going to deal with now are the so-called Bell states. So we are going to use this to discuss density matrices. We are going to use that one to discuss, let me just take that one out, matrices. We're going to use that to discuss entanglement, pure states, and mixed states, and more stuff. Plus, plus. So what are these Bell states? Now, these Bell states are states which are based on a 2-qubit basis. So we have the 2-qubit basis, which we discussed in the beginning of this lecture. This is an orthogonal basis, and it's a complete 2-qubit basis, which we could use to make a computational basis. So we have seen the states 0, 0. We have seen the state 0, 1. We have seen the state 1, 0 and 1, 1. So this is a complete computational basis. It's orthogonal, but the thing is that all these states are what we call product states. So all these states which you see here, these are all product states. So if you look at the first one, 0, 0, that is given by the product, the tensor product. When I say product states, these are the tensor products of the individual qubit states. So that means that everything I make here as linear combinations of all these states, they will actually you can actually write them as product states of the basic qubit states which we have. So these are product states. Now, when you then look at the first Bell state, this phi plus, this is defined in the following way. It's now a linear combination of these computational basis states which we had for the 2-qubit system. Now, this is a state which I cannot write as a product of the states 0, 0, 0, 1, 1, 0, 1, 1. So this is a first example of a state which we call entangled because it cannot be written as a product state. So this is our first entangled state. So this is an entangled state. And you can show that it cannot be written as a product of this basis state 0, 0, 0, 1, 1, 0, and 1, 1. Last year, we had an exercise on proving that this cannot be written as a product state of these states. If you're interested, I can bring that exercise back again. It's not difficult to show that. But these are called entangled states because they cannot be written. They cannot be written as a product of the computational basis states, comp basis states, zero, zero, 1, 0, 0, 1, and 1, 1. Now, you have met examples of this. If you are familiar with the atomic helium in the ground state, so an example which you have met of an entangled system. So this is atomic helium. If you take away the nuclear degrees of freedom and you only look at the electronic degrees of freedom. So if you take atomic helium, then the wave function for two fermions, psi x1, x2, where x1 and x2 contains spatial degrees of freedom and spin degrees of freedom. That is given by what's called a Slater determinant, but the spatial part of the wave function is symmetric and the spin part of the wave function is antisymmetric. So the wave function then looks like a psi z1s. These are the so-called hydrogen-like orbits from Bohr's atomic model. And here you have the spatial degrees of freedom are 1, and then you have a 1s. You can have two such electrons, even though they are identical particles, because you have the spin degrees of freedom. So you see that the spatial part of the wave function is a product state. So it's simply the tensor product. So actually, when we write it like this, we are suppressing the tensor product notation. Keep that in mind, eh? So every time we write something like this in a compact way, here we actually should have put in a tensor product. But then This contains now a part which goes like 1 over square root of 2. And then I have a state with, and I'm writing this as a spin up for the first electron, spin down for the second electron, minus spin down for the first electron and spin up for the second electron. This is total spin equal to 0. And this is the ansatz which is normally made if you take any course in atomic physics and you start looking at many-body physics. You often use this system as a kind of way to understand how you can set up an antisymmetric state. Now, you will see that this spin part cannot be written as a product, a tensor product of spin up and spin downs. These are also tensor products of the spin up for electron 1 and spin down for electron 2. This is a wave function which then obviously changes signs if you change the positions of the two fermions. But the spatial part is a product state. The spin part is what we will call in our new language here an entangled state. Because it cannot be written as a product of or tensor product of spin ups and spin downs. Does that sound okay? Another thing which we also should say here is that we would consider, if you know that the system is in the ground state, and this model is a good model, then you would call this a pure state. Because a pure state means that you know exactly what the system looks like. So we are now assuming that the two electrons are in the 1s orbit, hydrogen type orbit, and they have these spin combinations. So this is a state which is fully defined by these quantum mechanical degrees of freedom. And we normally call that a pure state. Like we would also call this one for a pure state because we have initialized our system to be in that state. So when you're running quantum computations on a quantum computer, you will often find ways or try to find ways to make an initial state in a specific arrangement. So you could obviously start with your system in the ground state of helium. And then you will start making quantum mechanical operations on the different electrons. So on atomic helium, this is much more difficult because the particles are indistinguishable and identical, and you don't know which is electron 1 and electron 2. Yeah? Yeah.
Essentially, the states are linear combinations of the first.
Yeah, yeah. So what we are doing here is we are making linear combinations of the computational basis states. But the whole thing is that you cannot write this one as a tensor product of these states here. And then we say that the state is entangled because you're building up correlations which would not be there classically. So you would not be able to make this type of state here classical. Okay. So this is a basis you would choose, right? No, exactly. That's correct. So this would be what I would call a pure state, right? So if you know that the system is in a ground state, and you believe in what people have been telling you that this is a good way to represent the ground state, and you know that the system is in a ground state, and if this is a good representation, you will say that this is my system. Now, when you're making a quantum computer, what you often do then, so let's have as a kind of digression, because this is important. So if you are using quantum dots, for instance, you could think of you having made a trapping potential here, and you have a set of states where the system can be in. This can be single particle states, but they can also be complicated many-body states. So I could trap a single electron, or I could actually have excitation degrees of freedom in a complicated semiconductor where I have zillions of electrons, but I've been able to single out specific states. And then I look at the states as in terms of quasi-particle excitations, like you did in many-body physics when you took that course, right? So then, if you now think of this system here, and this will be system A and system B. So experimentally, you could now assume that you're able to isolate and manipulate these states. And then you would typically then say that, okay, this will be bit 0 in system A. This will be bit 1. So you define a computational basis based on an experiment. So then here you would have bit 1 in system B and bit 0 in system B. So suppose now that you have some kind of experimental equipment where it's very difficult for you to move into states above these two states. So as I said, this could be a 1 electron state. You could trap 1 electron in a harmonic oscillator well, or this can be the result of complicated many-particle interactions. But experimentally, you see this state and that state, but you know that there is an infinity of other states. But suppose now that these are the states which are relevant with the equipment you have, and these are the states you can access with the equipment you have. Then you can make an approximation. And that approximation is that your Hilbert space is given by the tensor products of these two states. So where I is either 0 or 1 in either system A or system B. So if nature now is so that I can actually reduce my degrees of freedom to only these two states here and these two states here, then I can make a computational basis which looks like this. And I simply state, this is my computational basis. It can be a classic, you can think of this as a classical basis. Then I can make states. And clearly I could make a state now, which could be the ground state of the system. So that you could now think that the ground state of the system is you having one particle here and one particle here. And one of them could have spin up and the other one could have spin down. But you could then prepare the system as a product state. So that means that your ground state here, the ground state, could then be represented by 0A times 0B. So, sorry, 0 in system B. This state would be a product state and it would not be entangled. Yeah? No, go ahead.
So the first states represents some state from A times some state from B.
Yeah.
Yep,
exactly. So a pure state applies both to non-entangled states and entangled states. Because you can now say that I have defined my state. I know experimentally that the system looks like this. Okay. Then I can make another pure state. I can now say that I have constructed an excited state which is now simply some coefficients alpha 0, 0 plus a coefficient beta 1, 1. I can do that. You can actually realize that experimentally. And that would be a pure state. I know that my system is in this state. I know that the system A is in a linear combination of 0 and 1. And system B is in a linear combination of 0 and 1. But then I can define my state, and I know that it looks like this. And there are experimental ways to assess that I'm actually in this state. So this would also be a pure state, but this will be an entangled state, because I cannot write that one as a product basis of my computational basis. So, and the Bell states are examples of that. So let's take a closer look at these Bell states. So this was a small digression. So if we now look at the Bell states, we know that the 0, 0 is given by 1, 0, 0, 0, and the 1, 1 state. And now I'm skipping the tensor products. And I'm just writing it out here. This is 0, 0, 1. Then what I'm going to do now is when I'm setting up the states, I know also that I have another state, which is phi minus, which I can write as 1 over square root of 2. And then I have 0, 0, but I have a minus 1, 1. The negative faces are important, actually. Psi plus is given by 1 over square root of 2. And this is a linear combination of 1, 0 plus 0, 1. And finally, I have the psi minus, and this is 1 over square root of 2 of 1, 0 minus 0, 1. So I can show that these states, in the same way as I could make states which are eigenstates of linear combinations of poly X and poly Y matrices, instead of the 0, 1 bit states, I can show that these 4 states also form an orthogonal basis. But this is an orthogonal basis which is now entangled. And it cannot be written as a product of the computational basis states. Okay, so this is just a difference between the states, but there's nothing which hinders me saying that this is my new computational basis. So if you want to, you can show that. You can show that the other basis is also computational basis, is orthogonal and normalized, and that this is also an orthogonalized and normalized basis. We're not going to go into all those details. So I can now make a density matrix for the first state. So let's go back to this one. So this state which we have here, let's look at what the density matrix looks like. And let's run through the calculations. So we can now define the density matrix of this phi plus. And if I do the algebra, this should actually be 1/2. And then I would have 0, 0 plus 1, 1. And then I have the tensor multiplied with, so it's the outer product. So I have 0, 0 plus 1, 1. And this should result in a matrix, which is going to look like as follows. So when I do the algebra here, I will get 1/2. So it seems I'm a little bit slow actually, but I was hoping to do more than this, but we will have to postpone that to next week. Not that one. So that's my density matrix. And what you will also see when you square this matrix, this is going to be equal to the matrix itself. And the trace of that matrix, or plus squared, is the same as the trace of the matrix itself. And this one gives 1. This is a definition of a pure state. So the trace of the density matrix is equal to 1. Okay? So that was first component. And now we want to make a measurement. So suppose now we want to make a measurement of the qubit 0 in the state, obviously. So if you now think of the measurement part, and suppose we want to measure on qubit 0. So let's make a measurement where we now look at this specific component, which is given by the tensor product of these two states. And that means that if I now want to make a measurement on qubit 0 in system A, I'm leaving system B unchanged. Leaving it unchanged means that my measurement operator should contain an identity matrix for qubit 0 in system B. So this is now equal to 0 of A and then the outer product of 0 and A. But then I need to make a tensor product with just the identity matrix in system B, because I'm not doing a measurement on qubit 0 in system B. Suppose now that I am able to make a measurement in system A only. So the systems are well isolated and they can be looked at distinguishable systems. So I can actually set up a laser which I know acts only on system A. So I'm making a measurement on system A. And now I want to find the probability for what happens when I make a measurement on system A. So I have 1, 0, 0. And this is obviously multiplied with 1, 0, 0, 1. So when I set up my projection matrix, this is 1, 0, 0, 0, 0, 1. So you see the linear algebra pops up again and again and again. Okay? So that's what this is going to look like. And then I can now go back and set up the measurement as we defined earlier. So I could ask now, what is the probability of measuring qubit 0 in that system? So what I'm setting up now is the probability of this state phi 0. And now I'm having qubit 0 in system A. There's a little bit corny notation here. So I'm taking the whole system, A and B, and then I have phi plus, and then I have this P0, which I have defined now, which acts on qubit A. So if I do that, this is going to be equal to 1/2. So this is the only component which actually kicks in when you, because the 1, 1 component has, is going to give us just zeros. So I'm going to calculate 1, 0, 0, 0, 0, 1, 0, 0. And this is multiplied with 1, 0, 0, 0. And you see that if I take the state 1, 1, which is actually going to be given by 0, 0, 0, 1, you will see that since we have zeros here, that is going just to give us zeros. So the only possibility I have now is that when I do the calculation here, you will set that this is 1/2. So the probability for measuring this qubit 0 is equal to 1/2. Then you can repeat this and do the same for the probability of 1 in system A. And then you would simply take the state 1, 1. And in that case, you will also get 1/2. So these are the probabilities. So I see my time is running out here. And next week, we will continue this discussion with a discussion on the pure states, mixed states. And we are going to look at, because now we did the calculation on the whole system, then we are going to trace out the subsystem. So the thing which is interesting here is that we know precisely that if we are measuring out a qubit 0 here, the other state will be in a qubit 1. But when we now are going to trace out the subsystem, system A or system B, we will find something which is called a mixed state, which means that the system will be either in state 0 and 1, and we cannot tell precisely in which state it is. So we are coming back to these calculations next week, because now we have simply just looked at the probability. We performed a measurement on one of the qubits. And next week, we are going to use this density matrix notation, and we are going to trace out the density matrix of one of the systems. And then we are going to analyze the degree of entanglement of the subsystems, because that's something which you often use as a measure of entanglement. But now, what we did here was simply to perform a measurement, and we did not finish properly what I wanted to do. So we would need the first part of next week to discuss a little bit more about mixed states, pure states, and measurements on the states, traces of the full density matrix, and traces of the density matrix for a subsystem. And then we are going to link these to the kind of quantities we want to analyze and how we want to use entanglement. Okay, so I'm gonna stop here. That's okay.